What I propose we do now is a sort of anatomy of the different parts of a black hole. But since the black hole is nothing more than space-time itself, contorted, as Thorne would say, what we are going to do is a sort of anatomy of the different regions of space-time in the vicinity, in the neighborhoods of a black hole. I had started with the simplest case, which is a spherical black hole that is just sitting there and is a body so dense that it does not allow light to escape. Or put another way, a curved space so much there on the surface we call the event horizon, that what happens inside becomes disconnected from what happens outside. Now we are going to start to evaluate what happens, not there, but a little further out, where there is also very curious physics occurring. But let's start with the interior. Let's say that inside that event horizon there is a point where the laws of physics break down, where the inside in the interior of the black hole, at the center of the black hole, space is infinitely curved and the laws of physics do not hold. That point is called a singularity. Well, one can try to understand it, what it means for there to be a point where the laws of physics cease to apply, where the dynamics of a particle trajectories abruptly end. But since that is inside the event horizon, one might, for pragmatic reasons, say, well, let's worry about that later. Now let's think about the horizon and what happens outside. After all, we said the black hole can be sort of as this bite taken out of space. So let's think about what happens from the event horizon outward. First, let's say that the event horizon is proportional to the mass of the star. This is something that comes from Einstein's equations. There is a very precise and quite simple formula, which is that the radius of the horizon is 2 times the mass of the star multiplied by Newton's constant divided by the speed of light squared. The detail of that formula doesn't matter. What is important is to understand that the radius or the diameter of a black hole is proportional to its mass. That is, if I have a black hole with the mass of the sun, its radius is 3 kilometers. If I have a black hole with twice the mass of the sun, its radius will be 6 kilometers. And if I have a black hole with 3 times the mass of the sun, the radius will be 9 kilometers. It's proportional. If I double the size of the black hole, it's because it has at least a simple black hole that only has mass. Its mass is exactly proportional. The radius is proportional to the mass. Now then, let's think about a black hole. It has an event horizon. What happens inside can never affect what happens outside. But a little further beyond, at one point, 5 times the distance of its radius, that is 3/2 of its radius, there is an imaginary sphere known as the photon sphere. That region of space is outside the black hole, but it delineates 2 regions, inside the photon sphere, but still outside the star, outside the black hole. Between that 1.5 of the radius and the radius of the black hole, all light, every ray of light that falls there, will inevitably end up falling into the black hole. While the photon sphere outward, the rays that pass, end up escaping, so to speak, they don't necessarily fall in. That region, that sphere, which is, I repeat, 1.5 times the size of the radius of a black hole, a little outside the black hole, is known as the photon sphere and delineates the 2 regions where light rays skim and can deflect their path but escape from that region a little closer to the black hole where the rays inevitably end up falling into the star. This is known as the photon sphere. Now, a little beyond the photon sphere, now go into sometimes the Schwarzschild radius, sometimes it's 3 times the radius of the star. There is a distinct region known as ISCO by its acronym in English. But it is the innermost stable orbit that can exist. What does that mean? That in Newton's theory of gravitation, which we now know is not correct, Einstein's theory came to correct it. But it is a good approximation when the stars are not very massive or when they are orbited from very far away. But according to Newton's theory, one can orbit close to a star, for example, a black hole or anything else, as close as one wants, as long as one has enough speed to do so. Basically, if Mercury is going to orbit closer to the sun, it will go faster. That's why Mercury has a much shorter year than ours. In fact, recently, for example, planets in other solar systems have been discovered, known as exoplanets, which have an incredibly fast rotation and complete an orbit in only 16 hours. That's because they are very close to their star. Now, in Einstein's theory of gravitation, this is not the case. In Einstein's theory of gravitation, there is a minimum radius at which one can orbit stably. Inside it, things end up falling. They can orbit, but in an unstable way. Or if I want to orbit closer to the star, I inevitably end up falling. It is not a stable orbit. So there is a minimum distance known as ISCO, right? which is more further inside that ISCO, I cannot orbit stably around the black hole. That is important because black holes are then at the center. Then there is a large band where there is nothing, and only then can matter that is orbiting pass through. Everything that falls in here inevitably ends up falling into a black hole. Another thing, a curious thing, going back to the photon sphere, which is where light divides the region, where light ends up escaping the region. If you're a little further in, the light ray ends up falling into the star. If you place a light ray exactly there, that light ray stays orbiting as if it were matter too, very unstably. I move it a little and it either escapes or falls to the star. But if I place it precisely there in the photon sphere at that radius, which is 1.5 times the size of the star's radius, the light ray remains orbiting. The photon sphere is important because if somehow we could see a star placing it between something incandescent and us, we could see its silhouette drawn. But the silhouette we would see drawn is not the surface of the star, but that of its photon sphere. The photons, the light that would graze the black hole, would end up falling in anyway. So if one wants to truly understand the silhouette they would see of a black hole, they have to understand not only its surface, but all these regions, these photon spheres. So, as we see, the structure of space-time around the black hole is also quite surprising because it differs from what Newton predicted. It is no longer true that one can orbit around the star as closely as one wishes. It is no longer true that light does not orbit around stars. According to the theory of relativity, these two things do happen. Light can orbit around a star, and matter can also approach, but not as much as it wants to a star, only up to the ISCO, up to a certain region. Now, this is for one of the simplest black holes. Black holes can have, besides a given mass, a given rotation, and this makes everything much more complex. I want to explain what changes, but first a historical note, so that we can understand and appreciate how much more complicated the structure of space and time becomes when the black hole rotates. Let's consider that the first person who understood the solution to Einstein's equations describing a non-rotating black hole was, as we said, Schwarzschild in 1915-1916. In contrast, the rotating black hole's space-time structure was only understood in the 1960s. We are talking about almost 50 years later. The one who discovered it is named Roy Kerr, and it was Kerr who realized all the curious physics that appears on top of everything I just described when the star rotates. Let me clarify some fundamental things about Kerr black holes, no longer about Schwarzschild. Black holes that, apart from having a certain mass, rotate. Some essential differences are the following. First, stars, we see some senses. When the star rotates, it becomes oblate. Oblate means flattened at the poles. This, if you will, is somewhat intuitive. The star will no longer be spherical, it will be axially symmetric, but will have flattened poles. It is completely smooth, but flattened, it becomes oblate. Oblong is this, oblate is something flattened. It starts to flatten, and the faster it rotates, the more it flattens. That is the first morphological difference, if you will. Up to that point, it's anecdotal. It just makes things more complicated because, of course, it's much easier in equations to solve spherical things than oblate things. The equations, they become more complex. But that's all for now. Now, the point is that there are other things that happen when the star rotates. Initially, inside the event horizon, which will no longer be spherical, but will have that flattened shape like a hamburger, another horizon appears inside. Rotating black holes begin to develop inside the event horizon, another horizon known as the killing horizon, which is also unstable. Moreover, the point at which the laws of physics broke down, which we had called a singularity, when the black hole rotates, starts to widen and becomes a ring. There is still a singularity, but it is no longer just a point where the laws of physics do not apply inside, but rather an entire ring where they do not apply. So rotating black holes have these peculiarities, and outside of them, outside the event horizon radius, they develop another surface known as the ergosphere, which is no longer the photon sphere, it is another region. That ergosphere is a region that at the poles coincides with the event horizon, but outside, like a sort of orange wedge, it exceeds it a bit, and it's a region where if one passes through, one can manage to exit that region again, can escape. It is not yet having entered the event horizon, but it is a region where if one is inside, one cannot remain still. It is a region where no observer can be still. So all observers have to be rotating. And that is important because if you place a rotating black hole in the presence, for example, of some external electromagnetic field, for example. Today we know that black holes in galactic centers, for example, are immersed in a region where there are quite intense magnetic fields of not a few gauss, but quite a few. So, due to the fact that the field lines cannot be in equilibrium within the ergosphere, the combination of the rotation and the magnetic field in which the black hole is situated generates certain instabilities that produce two jets of energy, which I will talk about later when we discuss how to observe a black hole. So basically, what we begin to understand is that when the black hole rotates, space-time starts to become much more abstruse. In particular, and this is another effect that makes the theory of general relativity differ from Newton's theory of gravitation, is the following. If a black hole rotates in this direction, for example, it can rotate one way or the other, but let's suppose it rotates in this direction. Then it is easier for me to orbit along with it than against it. According to Newton's theory, orbiting a celestial body depends on the mass of the body and not on the direction it rotates. The direction of rotation was completely anecdotal. But Einstein's theory shows us that no, there is a kind of dragging effect known as the Lense-Thering effect, where the body tries to drag along with itself in the direction of rotation and not in the opposite direction. For example, if I have a ray of light and I go very close to the star and rotate along with it, nothing happens. But if I go very close to the star and rotate against it, it ends up convincing the light ray to change its direction and start rotating with it. That makes it so that if the star, you are looking at a star and it rotates in this direction, and I have a light source, for example, at the back of a galaxy, it is projecting its image onto the dark silhouette that you are going to see. This silhouette will not be symmetrical even if it rotates like this. The star is symmetrical, but since it will drag the light from one side differently than the other, you will see that the silhouette, despite the star being symmetrical, appears oblong, but equally on both sides, it will acquire a sort of nephroid shape, like a kidney. So this is important because, again, if we are going to observe these silhouettes, and today we have photos of these stars, scrutinizing this shape will require us to understand very well what the geometry of space and time is and how that silhouette will deform based on all these effects that light undergoes when it is near them. So this is essential because it is the first step to understanding what we might want to observe or what we might expect to observe if we now astronomically venture to see if these celestial bodies, which we have so far talked about as a theoretical prediction of Einstein's theory, truly are in the sky. This is clearly a problem because we are talking about invisible celestial bodies. So what does it mean to see? How is it possible to see? We will not be able to have direct evidence of them. We will not be able to see the star because it is by definition invisible, but we can see how light and matter behave around them. That is why it is essential to first make this sort of footnote and try to understand how abstruse the dynamics of matter, radiation, and light around these stars can be.